Hello everyone. Welcome to YouTube channel Energy Exergy Theory Applications. I am Tatiana Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. Lecture 3 on engineering thermodynamics is dedicated to thermodynamic cycles and definition of energy efficiency. The topic of thermodynamic cycles is very wide. Unfortunately, not always very properly discussed in the books of thermodynamics. But I always emphasize on the all aspects of thermodynamic cycles because, by my opinion, thermodynamic cycles, it is not only the application of engineering thermodynamics to the practical task, but also creativity of engineers also lead to thermodynamic cycles. Because if new thermodynamic cycles will be developed or existing improved, we significantly can improve energy efficiency. And energy efficiency also required a very deep discussion because at present, unfortunately, the term energy efficiency not always properly applied and I mean for engineering aspects, and definitely can bring quite a lot of misunderstanding in interpretation of the results. Let us repeat the first law of thermodynamics. It is the principle of conservation of energy. So energy can be stored within the system, energy can be transformed from one form to another form, energy can be transferred from one system to another system or from the system to sorting. And if we would like to proceed with energy analysis, we need to write energy balances. We already discussed that. Analysis and corresponding balances. And energy balances should be written or applied only together with mass balances. Without mass balances, we cannot proceed further with energy balances. In the previous lecture, we already covered energy balance for open system. Now we will discuss the energy balance for the closed system. For engineering thermodynamics, closed system associates for us with the cycle. And we already discussed the definition of cycle. If system is going from one initial state through the series of the process and return to the same state, we have a cycle. And depends on the direction of the processes, all cycles divided to two big categories. It is direct cycles and inverse cycles. And the word direct or inverse mainly associated with the direction of cycle in thermodynamic diagrams. For example, here we have TS thermodynamic diagram. And the mass balance for the closed cycle, mass is constant because according to the definition of closed system, matter, so working fluid, cannot cross the system boundary. According to the energy balance of the closed system, so it is cycle, if system returned to its initial state after the passing set of the processes, the net change in energy is equal 0. Net change. So it means that balance is written like that. Work of the cycle plus heat of the cycle is equal 0. So it is well-known equation. Now let us discuss each term. What means work of the cycle? Work of the cycle, it is the sum of all works supplied to the cycle and rejected from the cycle, or better to say work applied to the cycle and work produced within the cycle. It is called work of the cycle. Similar, we can discuss about heat of the cycle. All heat transfers to the cycle minus all heat transfers from the cycle. And we can show it graphically. So let us assume that we have a cumulative stream of all work supplied, all works produced, all heat. Heat or heat rates, or instead of work we also can say power, does not matter now. For us both are okay, and all heat transferred through the system boundary. If we will be absolute precise with thermodynamic terminology, of course, it will be energy transfer in form of work and energy transfer in form of thermal energy. That will be absolute precise thermodynamic terminology. So we have equation that net charge of energy of the cycle is equal 0. And now this simple equation we will rewrite according to the mathematical rules. We can write minus work of the cycle is equal heat of the cycle, or we can write work of the cycle is equal minus heat of the cycle. Both are correct. From mathematical point of view, both equations are correct, and one is not alternative to other. But for the physical meaning, for thermodynamics, that will be already different. And now we will discuss. What means minus work of the cycle? It means that work supplied coming in is less than work produced, so going out from the cycle. Therefore, we have here minus. But for heat supplied is higher than heat rejected. So thermal energy supplied is higher than thermal energy rejected from the cycle. This is first case. The second case, we have work supplied is higher than work produced by cycle or removed from the cycle, but we have minus heat or energy in form of thermal energy in form of heat. Heat supplied is less than heat rejected. So now how it will affect to the configuration of cycle and analysis of the cycles. Again, the same equation. If work is negative, work of the cycle negative, as we already agree, according to European rule, if energy transfer coming from the system, it means that it is produced within the system. So work is negative, means that within the system, work is produced. And this is the effect of the closed cycle. But heat of the cycle is positive. If work of the cycle is positive, it means that for the realization of cycle, work should be supplied. And amount of work that is supplied to the cycle, maybe something also is produced, but nevertheless supplied will be higher than work produced by cycle and removed from the cycle. And heat of the cycle is negative. It means that we will supply less heat that we will reject from the cycle. Let us remember the 4 blocks when we discussed it about engineering. We had energy transfer, we had working substances to get its thermal design, after that engineering design and operation. Now we will discuss thermodynamic cycles. Definitely operation and engineering design not interesting for us because it's only thermodynamic concept of cycle, and at present working substances or working fluids also not included to the discussion. So it means that thermal design and all our thermodynamic discussions will be only limited to the block energy. So now the only interest for us how heat is supplied to the cycle and rejected from the cycle, work supplied and work rejected, so means that work produced within the cycle. When we discuss about work, it is more or less clear for us because work is only work and there is no any other categories that should be discussed behind the work. But heat always associated with transfer of thermal energy. It means that for heat we need not only amount of heat but also temperature level at which heat transfer is taking place. And in thermodynamics, there is a concept of thermal reservoir. It is absolute theoretical concept. In real life, thermal reservoirs don't exist. And we need to introduce this concept for thermodynamic analysis of the cycle. So thermal reservoir, it is a special kind of closed thermodynamic system, hypothetical closed thermodynamic system. And what do we know about thermal reservoir? That temperature of thermal reservoir is always constant, regardless how much energy we will take from this reservoir or how much energy we will reject to this reservoir. It will not affect to the temperature. Temperature always will be constant. It means that this thermal reservoir is of huge size. So we will discuss two thermal reservoirs. One in red color always will be associated for us with higher temperature, and in blue color will be associated with the lower temperature. Here I would like to bring your attention. We will not discuss about hot reservoir or cold reservoir. We always will discuss only relative hotter and colder. This is very important for us. So now we will deal with thermal reservoirs. The only thermal reservoir that is more or less close to real life and we can understand what is it, it is environment. Many years ago, people assumed that our environment, regardless how much energy we will reject or take from the environment, temperature will be always constant. Okay, after Paris Agreement and all these ecological issues, environmental issues, but better to say we know that unfortunately temperature is not constant of real environment, so which is called surrounding in thermodynamics, and temperature is continuous growing. So it means that even surrounding, we cannot assume that it is really ideal thermal reservoir. Okay, this is real application, and now we will return to thermodynamic analysis. Let us assume that we have a thermodynamic closed system. Temperature of this system is constant, and this temperature will be temperature of the environment. And already from the beginning, temperature of the environment, we will use the nomenclature for that as T0. That will be very helpful when we will move to exergy analysis. Let us stay already with this nomenclature. Everything which is related to environmental conditions will have subscript 0. Okay, it means that we will have one reservoir which is hotter with temperature higher than environmental temperature, so it means hotter reservoir, and one reservoir will be with temperature that is lower than environmental temperature. Here it will be colder reservoir, but since we are already dealing with environmental conditions, we can say really that red reservoir it is hot and blue reservoir it is cold. This we can already use absolute definitions. Okay, and now we have three temperature levels: environmental, hot, higher than environment, and cold, lower than environment. And we can have the following energy transfer. We can have heat, thermal energy transfer, that will be better to say, from a higher temperature level to lower, and lower will be environment. And we will produce work, and we will realize direct thermodynamic cycle, and we have two possibilities to transfer thermal energy from the lower temperature level to the higher temperature level, from the lower, even if it is environment, to higher temperature level. Work should be supplied, and realization will be of this cycle will be within inverse thermodynamic cycle. So now we can see that for thermodynamic analysis we have one direct thermodynamic cycle and two inverse thermodynamic cycles, but in operation with different temperatures, between different temperatures. The first cycle, the first thermodynamic schematic. This when heat transfer we have from the hotter temperature level to the colder temperature level, it's called heat engine. So heat engine, it is thermodynamic term for the closed thermodynamic system where direct thermodynamic cycle is realized, and therefore we have work produced that can be transferred from the system to surrounding. We already discussed all these equations, and for direct thermodynamic cycle, work has negative sign, so means work is produced transferred from system to surrounding, and heat is positive, means that heat supply is higher than heat rejected to the environment. So heat supply higher value, heat reject lower value, and the difference between these two values is work produced by the cycle. The rate between work produced and work rejected to the environment, it is already a matter of discussion which cycle exactly realize it and also which working fluid will be used. At present, it is not important for us. We're discussing only thermodynamic concept. And I would like to bring your attention that direct cycle and power cycle, it is synonyms. So some authors prefer to write direct cycle, some authors prefer to write power cycle. Direct cycle, it is mainly thermodynamic term. Power cycles, of course, it should be plural because we have many cycles. It is already for engineering application. And heat engine, this term that I mentioned at the beginning, it is only thermodynamic term. Heat engine does not exist in real life. You cannot buy heat engine. If you will Google, for example, heat engine, you continuously will find the only that it is thermodynamic concept. What is the behind heat engine? All thermodynamic cycles, direct thermodynamic cycles, where power will be generated. So heat engines, it is power plants, it is internal combustion engines, it is everything different. So power plants, different cycles, everything can be described as heat engine if we discuss purely thermodynamics. Two inverse thermodynamic cycles. For both cycles, regardless if one cycle operates between temperature below of the environment and environmental temperature, or other cycle operates between environmental temperature and higher temperature, both are inverse cycles and will be valid the following set of equations. Work of the cycle is positive, means that work should be supplied to the cycle, and heat of the cycle is negative. It means that we will supply to the cycle less heat that we will reject from the cycle. And we have two terms and also engineering systems that operate according to inverse thermodynamic cycle. First is called refrigeration machine, between temperature below of the environment and environmental temperature, and heat pump between temperature of the environment and higher temperature. Refrigeration machine and heat pump, I repeat, it is together thermodynamic concept, but also a technical unit. So if we would like to buy refrigeration machine, we have a lot of offers. Many companies over the world can offer us refrigeration machines, different design, different type, different working fluid, but everything will be called refrigeration machine. And the same will be for heat pumps. So let us continue our discussions with the cycles. Let us look a little bit deeper to inverse thermodynamic cycles to avoid any misunderstanding in the future when we will discuss refrigeration machine. So we can see that for refrigeration machine, heat from the lower temperature level is transferred to the higher temperature level. So it means incoming heat is lower than outgoing heat, and outgoing heat rejected to the environment, it is the sum of incoming heat, and in the terms it is refrigeration capacity, and work supplied to the cycle. In heat pump, we have similar equation. Work supplied to the cycle, heat is transferred from the lower temperature level, which is environment, and transferred to the higher temperature level. So amount of heat that transferred to the higher temperature level, it is amount of heat that we will take from the environment plus work. Now we are reaching the topic of efficiency, but I would like to start this topic from the previous definition. So let us start from the very beginning. We have the word performance, and we know what means performance. We know linguistical meaning, and we know the application of the word performance in our everyday life. When we say performance, we don't need to give a numerical value. Performance can be of students, for example, performance can be economic performance, can be environmental performance. So but the word performance has very wide spectrum of applications. But we need to apply the word performance in thermodynamics and give the technical meaning for this word. So let us start from the beginning. What means performance? Performance, if we would like to calculate this value, it will be the positive effect that system will generate over driving resources that we need to spend in order to generate this effect. Definitely, if we are discussing in terms of energy, positive effect should be in energy form. It can be heat or work, and driving energy also should be in energy terms as work or heat. So it means that if we have energy conversion system, among all streams, energy streams coming into the system and going out from the system, we always should find the streams associated with positive effect and with driving energy of this system. So regardless if it is direct thermodynamic cycle or inverted thermodynamic cycle, principle will be absolutely the same. Let us assume that we have a system where 3 energy streams are coming and 3 energy streams are going. Let us assume that stream 2 in red color will be associated with the driving energy for the system, and this blue stream, it is stream outgoing stream 1, will be associated with positive effect. What to do with remaining 4 streams? In energy analysis, these 4 streams will not be counted. So these streams, of course, we need to write because we need to fulfill energy balance, but these 4 streams will not participate in definition of efficiency. And I repeat, for efficiency, performance, it is logic definition, and efficiency, it's already, if we would like to calculate something, it will be only positive effect in energy terms and driving energy. In literature, in different years, in different languages, we can find the term energy efficiency, sometimes thermal efficiency, it is already old term. We can find also first law efficiency, means energy efficiency, because it's based on the first law of thermodynamics, and we also can find the term coefficient of performance. Let us discuss all these 3 terms more in detail. Performance is called energy or thermal efficiency for heat engine, so means for all energy conversion systems operate according to the direct thermodynamic cycle. Energy efficiency is always in the limit between 0 and 1. Definitely it never can be 1. Coefficient of performance, it is also energy efficiency. That is the term is used for refrigeration machines and for heat pumps. So for energy conversion systems that operate according to inverse thermodynamic cycles. Now the question, why for heat engines, for direct cycle, we have one nomenclature, and for inverse cycles, we have another nomenclature. We have no even Greek letter for that. We have simple combination of 3 words, coefficient of performance. The answer is very simple, because thermal efficiency is always between 0 and 1, and coefficient of performance for refrigeration machine is varied between 0 and infinity, and for heat pumps between 1 and infinity. So in order to avoid any problems with the understanding of the term. And for very complex systems where both cycles are involved with direct and inverse, we also will discuss such systems. We will use mainly the term coefficient of performance, because this value can be higher than 1. And as I mentioned already, very popular also can be the term first law efficiency. In this moment, first law efficiency has no over nomenclature and can be used nomenclature from already 2 cases that we covered. When we discuss about energy efficiency and cycle efficiency, 3 thermodynamic systems, we already know how to calculate these values. But now, please pay attention. During our discussions, I never mention working fluid that should be used. Topic of working fluids is not included. Definitely, working fluid should should exist within the cycle, but properties of working fluids not included to our discussion. We did not discuss which processes form the cycle, and even number of processes. It is 3 processes, 4, 5, or even more. It was irrelevant for us. This topic was not included. And the last topic that was not included, we did not discuss if each process is theoretical, ideal, or real. That was also not included. So it means that when we discuss about energy efficiency or coefficient of performance, these three categories: working fluid, which processes and how many processes form the cycle, and if cycle is real or theoretical or ideal, these topics are not included because we discuss it only the entire system, energy in, energy out, energy in, energy out, work supplied, but we did not discuss thermodynamic processes within components. Now, to make our discussions clear, one more time, I will repeat that efficiency of the heat engine, it is work produced by cycle divided by heat supplied to the cycle, because driving energy, it is heat supplied to the cycle. It is not the difference between heat in, heat out. No, only heat supplied to the cycle is it driving energy, because if this heat will not be supplied to the cycle, cycle will not work. We will have no driving energy. And positive effect of the cycle, it is work produced by cycle. Similar we have for refrigeration machine, but for refrigeration machine we have a positive effect. It is refrigeration capacity, and driving energy, it is work supplied to the cycle. For refrigeration machine we have unique case that positive effect is the heat transfer to the system, so it is incoming energy transfer to the system is already positive effect of the cycle, but it is unique case, as I already mentioned. And COP of the cycle, core refrigeration capacity over work of the cycle. Similar equation we can write for heat pump, but in heat pump, positive effect, it is heat produced at high temperature level. So for a heat pump, positive effect, it is energy stream going out from the system to the higher temperature level, and work supplied to the system, because we're discussing inverse thermodynamic cycle. And if you like this our lecture, please give a like to this video. Please share this link with your colleagues and subscribe our channel. Our next lecture, lecture 4, will be dedicated to the second law of thermodynamics and concept of irreversibilities. Thank you.